In this tutorial, I think what we're going to cover is we're going to cover more type classes. That's it. So functors, applicative, monad, and monoid. So I'm going to do this properly with cable in it. Oops. Because we're going to be doing I/O now. Finally, I/O. We can actually build our programs and run them. So let's do that. So first thing to mention, I should have loaded the REPL actually, because we're not doing I/O yet. We're still a little bit away. This tutorial, but a bit of work to cover first. Let's start with monoids. They're the easiest. So there's a class called monoid, and its definition is something like this: semi-group M to monoid M, where mempty is of type M, and mapend is of type M to M to M. So this is the monoid type class, and this is the first properly abstract type class that we've looked at. We've only looked at ones that they're easy, like number, equality, but this is monoid, and it has a dependency on a type class called semigroup. You know, we're digging deep into mathematics now. We're not actually. The Haskell compiler writers are, which is why they have all of these deeply mathematical names. But you don't need to worry about really what these things mean. Now, mapend has a default implementation like this. And this infix operator we find in semigroup. We have to define in semigroup. So what is a monoid? So a monoid is a thing, a type, that has a unit type and also has a single binary operator. So lists are of type monoid, and I'll show that in the REPL again. So 1, 2, 3, and then that, and you see we have 1, 2, 3, 1, 2, 3, and we're using mapend in the middle. I could have written mapend. There we go. 1, 2, 3, 1, 2, 3. Now, there are some rules for what makes something a monoid. So, if either of if either of the arguments to mapend is mempty, the result has to be the same. As it is in this case, because lists are valid monoids. And that's all it really is. If you want to define your own monoid instances, you need to define an instance for semigroup, but that's really easy because semigroup only has one function, and that is the binary operator there. So that's it for monoids. I only really wanted to mention them because I wanted to show you that there's sort of a higher level of thinking when it comes to type classes. So examples of other monoids. You could probably say that integers can be made into a monoid, with mempty being 0 and mapend being plus. You could also say that it's a monoid with 1 and multiplication. Lots of things can be monoids. But now for the more interesting, and something that you'll actually use a lot. So there is a class called Functor. 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 And this is what we have in functor. fmap is of type A to B to FA to FB. Now this looks really similar to something we've come across before. If you're thinking that looks like map, you'd be completely right. If I go map +1, the classic, to 1 to 10, I've done this many times, we get that answer. If I do fmap, it is exactly the same. Fmap is map for, is map for lists. I wonder if this works. Capital F. Hey, now we're getting somewhere. So sometimes you can go :info, and then something. Like, for example, I did functor here. And this is quite useful. So it said the type functor is of... Ignore this for quite a few tutorials. But here we have the class definition of functor. So we have fmap, which I showed you. We have these other two things. So this is like... What is this? You can ignore that. It can derive that. And here it says minimal fmap. And that means that a minimal definition of functor, you only have to give fmap, which is what I was planning to do. And here it shows you some instances. It doesn't show... Oh, there. It shows that list is an infinite, is an instance. Cool. Handy to know. Right. So we are going to use fmap. So before we made this data type called, we called it error, but I think failure this time seems nicer. We made this in the data type tutorial, so I think that was tutorial 3 or something, I don't know. You can find it. And we said it was either fail, or we said error, or OKA. Now, I'm going to explain fmap by defining fmap on fail. So let's look at this. So here we have a function. I think the best way to think of fmap is to actually put in the implicit brackets in the type. So fmap maps functions to functions. Okay? The category theory, they'd say a functor is a morphism that maps morphisms to morphisms. So this is our input function and this is our output function. And you see what it seems to do is it adds this context. And that makes sense. So we have sort of the category of functions and the category of functions on lists, and you can see the similarities. So our +1 was of type A to A, and we turned it to list A of list A. And we can do this with all sorts of things. So let's do it with failure. So instance functor of failure A. I'm going to comment this out again because this conflicts with the Haskell definition. Where fmap f of OKX equals OKFX, using that $ again, and fmap f of fail equals fail. So, what have I done? A kind error. My bad. How do I explain that one? It was expecting a type that took in a parameter. So when I gave it the parameter, I saturated it by accident, and I wasn't meant to. Anyway, there we go. I now have fmap defined for failure. So let's try it out. So if I go fmap +1, let's look at the type of that. So you see it takes a functor and a number, and it makes the function fb to fb. So fmap plus 1 of, let's start with fail, is fail. And fmap plus 1 of OK6, it's going to be OK7. Now this is a really, really, really useful function. What it does is it allows us to write very general functions, like plus 1, that operates on all numbers, and then without having to worry about the context, we can move that function into a context. We can lift it into a context. So I lift this into sort of the erroneous context. I now have a plus 1 function that is safe. It won't plus 1 on failed values, it'll only plus 1 on valid values. So it's very, very handy, and it's used a lot. Often it's used in infix form. So just so you know, my font, it's that, but without the spaces. Okay, 6, same value. So it can be used in infix form as well. So that's functor. So next, easy now, Vim, bit eager. Next, let's look at another class, and this is applicative. So it takes, so it has so all things that are applicative also have to be functors, and that is expressed in its definition. So we have two functions this time. Pure, which is of type a to fa, and we have this infix function, which is also known as app, which is of type fa to b to fa to fb. So it's a really interesting type class, this, and it's not always obvious what you use it for. So I might. It's really fun when things come up, but thinking of examples that are quite simple might be difficult. But let's try it out. So, wow, it just let me compile that. Maybe I spelled applicative wrong. Who knows? I'm going to comment down anyway. So, let's play around with pure first. No. I need to give an instance of failure for that. So instance applicative failure. And I can define applicative because I have an instance for monad. So pure is easy enough to define. So I just wrap it with an OK. I can, of course, remove these two X's. It's called pointless programming, when you program with as little variable inputs as possible. And then this one is always a bit tricky. So we have OKF applied to OKX equals OK fx. And then we have fail applied to anything equals fail. And we have anything applied to fail, which equals fail. So you can see it has very similar error handling properties to just like fmap. So let's think of an example. Okay. Somewhere where this is used a lot is type constructing. So let me think about this. Yeah, so how am I going to do this? let's make a type. Let's go data person equals person string int. I don't know. Maybe that string is their name, their age, and their ID. That will do. Deriving show. So say I had a bunch of computations that could fail. And I want to construct something of type person, but any of the computations to get that data could have failed. Maybe they were erroneous database accesses. In which case, I could write this code. So person applied to OK, and it was a string. James, I'll do me. And then we have this applicative thing. OK, and then it was age, so 21. And then another applicative thing. OK. What's my ID? It can be 10. Okay. And if you do this, you see it returns OK, person James 20. Okay, it's got the person. It's all correct. So what's going on here? Well, let's decompose it by looking at the types. So the type person is of type string to int to person. It's a data constructor. And now we're going to fmap that to OK James. And this is exactly what you would expect. So we have this string, this OK string with fmap. It returns failure int to person. And then we just keep on going. We could apply if we like with error. Oh, it's not error anymore, it's fail. And, oh, let me get rid of that T. Oh, no instance of show. It can't show the function. I'll just put the other two in. So you see, if any of them fail, the whole thing fails. That's interesting, you know? It's really handy for that. And you can kind of see what the infix is doing in this case. It's building up this person inside the context of failure. So really handy, really handy. And now for the big boy, we're going to go to monad. So we'll look at the class. So class and applicative is a dependency. So return is of type A to MA, and return has a default definition, which is pure. And then there's a fun one now, and that is MA bind. Now, excuse my font, it's those characters without a space. To what am I doing? This is a definition. I need to put it in brackets. So you have this infix here, which takes in a monad. It takes a function which is A to MB, and it returns MB. Now there are so many things that are encapsulated well by monad. It's incredible. It's incredible how many things. There are some monadic laws that might be good to know. Laws like the maths. So, for example, return x bound to f is the same as return f of x. So that's good. Fx bind return equals fx. Oh, and then there's the weird one. So f bound to g bound to h equals, so the brackets go like this, I think. Let me quickly work that one out. So we have xm, so no they don't. They go like this. Yep. Apologies. So that is the same as f bound to lambda x gx bound to h. So if you're interested, those are the monad laws. You can prove them out monads if you like. What tends to happen is you really struggle to define the definition of a monad if it happens not to be a monad. But if you really want to be a top-notch programmer, you'll go ahead and prove that those that your monad types adhere to those rules. But anyway, that was a digression. So let's think about a good example. So we can also we can say that our failure type is a monad as well. So instance monad failure, cool, where, before I forget, let me comment out that. So we don't need to define return because it equals pure by default. We just need to define bind. So bind is really great. It's okay, x bound to f equals fx, and error, no, it's fail now, fail bound to f equals fail. And that's our definition of monads, so of bind at least. So let's try and work out what this does, or at least what we can use it for. It's quite obvious what it does. It does what I wrote it does. So I can chain together functions that have no context, no error context in this, but produce an error context. And I can chain these together. And this massively simplifies my programming. So, for example, do you remember we did that safe divide function? And it involved a huge number of pattern matching cases. Let's define it again. Safe divide is of type failure int to failure int to failure int. So safe divide. This time we're going to give it inputs like so. We're not going to bother pattern matching on them. We're going to go xm binds to, and then I'm going to put that in a function. I'm going to bind that to a lambda function. So actually an interesting thing to show you would be signed holes. So if I just write underscore somewhere in a Haskell program, it gives me this error where it says found hole, and then it tells you the type of that hole. So int to failure int. Interesting. That really helps when you're writing complicated functions like this. So anyway, I'm going to bind that to a lambda. So now what I'm going to do, I'm going to do this on a new line, is I'm going to take ym. In fact, maybe I can make them a line and that would be satisfying. Ym. And I'm going to bind that to a lambda as well. So thinking about scope, where my cursor is now, I have access to both x and y. Now let's think about what we've done so far. So if xm is fail. Let's look at our definition. The whole thing will fail. It won't bother reading any of that. It's just going to fail. Perfect. But say XM is okay, it's going to move and it's going to bind whatever is it, okay, X is now X. And we can move on. Now, if this has failed, the rest of it's going to fail. But if it's okay, we now have whatever the okay value was in Y. And now, all I need to do is I need to check to see whether Y is 0 or not. So if Y equals 0, then fail. Else, return X div Y. Now this is horrible. This code is. Let's align it like this. I've not really thought about the alignment here. Sort of a weird shaped function. Let's see if that's fine. So safe divide. Okay 10. Okay 5. I get okay 2. Now if I try and divide by 0, it's going to fail. And if I try and divide safe divide okay 5, bracket that, it's going to fail. Great. And if I change that back, there we go. So it has the functionality we want. Fascinating. Fantastic. But that's only one sort of monad, and this is a very simple monad. So this monad that I've described is actually the maybe monad. So in Haskell, there is a type that's like this, and it has a better name than what I was coming up with. Maybe A equals just A or nothing. So that's the type we basically recreated. And that has a functor, monad, and applicative definition instance already built in. But we can do so much more with monads. There are so many different monads out there. So let's look at some of them. So lists are monads. So say I have the list 1, 2, 3, and I pipe that into a function. What function should I pipe that into? It has to be a function that takes in an integer and returns a list of something in order to fit the definition of bind. So say I had a function that just doubles, you can see what that does. I then get 1, 1, 2, 2, 3, 3. So what it does is the definition of bind on lists is it runs this function on all of them and concatenates the result together. So that's an interesting one. What else? Well, there's the big boy. There's IO. So we're going to go over IO later. We're going to sort of derive it from first principles, I think. So next tutorial, I promised I'd do GUI stuff, and we will do GUI stuff. After that, I think what I'm going to do is I'm going to look at building interpreters. I think we're going to build an interpreter. So I'm going to go through... it's very easy in Haskell, you see. So I think we're going to do interpreter stuff. And at that point, I'm going to derive this from first principles. And it's a bit of a whoa moment. So I'm not going to go into how IO is defined, but IO A is a monad. And so this line putstrlen, or print string line, is of type string to IO unit. So unit is just it's like a placeholder type. It doesn't really do anything. But we can now kind of extend this. So if I bind that to a function that ignores its input and then does something else, put strline hello world, then our main function now prints 2 lines. hello Haskell, hello world. We're getting somewhere now. So there's sort of a shorthand for this, and that is if we want to ignore the result of the previous thing in the monad, it's just 2 greater than signs. So that's one shorthand. There's another interesting shorthand that would make this code a lot clearer, and that is do notation. So you should use do notation as little as humanly possible. But for things where you're binding to lambdas a lot, it is a lifesaver. So do, and this is some extra syntax in Haskell. If I can, you know what, I'm gonna shift this in. What am I doing with my life? If y equals 0, fail, else return x div y. I need a then, and I'm going to new line this for ease on the eyes. So this is actually completely equivalent. It is syntactic sugar for what we did before. So instead of doing all of those nested binds and lambdas and rubbish like that, we can kind of, this sort of, it extracts the monad, the value in the monad, and sticks it in x, and this extracts it from xm and puts it in y. And then you can kind of think of this as sort of almost, it's a bit like imperative programming. But it has the behavior of your monad. So if xm is fail, the rest of it won't be run. This is exactly the same as what we wrote before. So you'll see safe divide still works as expected. But it's very useful for I/O. When you do it in I/O, it is just like, in a way, imperative programming, but slightly more inconvenient. So if I just put 2 things one after another, that's the same as joining them with the 2 greater than signs. So main here does exactly what you'd expect. Great. So let's talk about a bit more input and output. So there's the whole classic. Oh, what's your name? My name is James. Oh, hello, James. We'll do that. So print line. Hello. What's your name? And then we'll go in S, read line, I think it is. And then we have to replace this with hello ++ S. Oh, I wrote a capital by accident. Oh, maybe it's readln. Let's see. So main, what's your name? James. Oh, what have I done? Oh, it is readline, but I've got it in the wrong import system. System dot environment, maybe? No. Oh no, it's getLine. Oh, I apologize. Let me fix this. GetLine. There we go. So main James. Hello, James. We of course could have written that using the other syntax. So I could say getLine, and then I could bind that and go probably to a lambda x x. I can do it like that. Works exactly the same. And that's I/O. So if I wanted to, I could cable v2 build. It will go and build it, and then if I can go cable v2 run. Hello, what's your name? James. Hello, James. I can do it like that, or I can find the executable and run it that way. Yeah, we're getting there. So I alluded by accident to system.environment. Import, mind your indentation, system.environment. That's going to let us do some more fun things. So if I go args, get args, that's going to get all the command line arguments that followed the call of my program. I can then print args. So what print does is print takes anything that's showable and prints out the show function for it. So main does nothing because I gave it no arguments. I could give it hello world. I can run, so what's this called? Tutorial 6. Hello world. I can run it, build it and run it properly. So we're compiling it here, and it works in exactly the same way. We're building proper programs now. They're not useful yet, but they're proper. Anything else? There's a fun one. If I get back into the REPL, called interact, and it takes a string to a string and outputs something of type IO. So if I go so string to string, reverses of type string to string. So if I make my function interact reverse, and let's build that, let's run it. So we're running it now. If I type hello, I thought it would reverse it. Oh, D maybe? Yes. You can see it reversed the input. D is D sends an end of file thing to an end of file character. Control D to the application. So as soon as the application finished, it yeah, I wonder if I go echo hello and pipe that into cabal v2 run. There you go, it reverses it. So what I suggest you do is use Google now that you know how to use Monads with I/O, and you can work out how to read files, write to files, loads of different I/O functions. But at this point, you can actually write functional command line applications. And next session, we will work on graphical user interfaces. Cool, so that's all for this video.